Okay, so good morning. Today we are going to study the physical database design. So in the whole semester so far, we kind of study how to design a database at high level using ER diagrams, and also how to organize data and represent data using the relational data model. And then we study the relational data model programming, SQL programming. And today we actually will kind of follow this path. So means that once we have a relational database schema ready, how we can turn them into a physical database. So the key topics in this chapter will include physical design strategies. We're also going to discuss views, how to build index, and also we're going to deeper into the index structures. So the physical design basically involves the process of transforming the entities into tables and the real-world instance into rows or records into the table, and how we turn the attributes into columns, table columns. So when we perform the physical design, we should consider several kind of aspects. For example, how to translate entities into physical table. I think that's pretty straightforward. So pretty much, for example, you create a table according to a relation schema. And then you also need to specify which attribute or set of attributes will serve as a key for that table. Then, and I think the other consideration is that how do you define the data type and the format for each attribute? Okay, although we may have multiple attributes, they all defined as a char string. Then we need to decide the size of the char string. Whether like a name field, we can define that the name field has no more than like the 50 characters or even the 25 characters. For the address field, maybe no more than 100 characters and so on. So you should have that consideration when you specify the physical format for each attribute. And also we're going to consider what indexes we want to define on the tables. So indexes actually is a data structure. So its main purpose is to speed up the query execution time. So it helps us to quickly locate the tuples or records in the physical tables. And sometimes we also need to consider whether we need to create views. Those views should be defined on a table or maybe defined based on a SQL query. So views also provides, I think, the two main purposes. One is to kind of quickly return the query result. So in other words, if we can predict certain queries are frequently asked or requested by the end users, we can create views based on those query results. So when user's query come, we instead of execute the query on the fly, we just pretty much go to the view table to return whatever results to the users. Okay, so that view basically contain the pre-calculated results of some queries. And so in this case, views can help us speed up the query execution time. The second purpose, I think I have discussed several times in the classes already, is trying to kind of restrict users' access to the base table. So we know that in the database, base table contains the information, source information that the whole database rely on. Okay, and for the base table, if we assign the access rights to the base table to the users, potentially it can be risky. So if the user is not experienced kind of programmer or is not aware of some security restriction, then the user might perform some queries or actions on the base table that cause the kind of, the data become dirty or invalid. So that's why instead of allow the users direct access to the base table, we can direct them to the views so that views, depending on how we define the views, so views can restrict like which columns of a table that a user can access. Okay. The last one is denormalize the table. So it's actually contrary the concept of the normalization. So we're going to discuss them one by one. Okay. So for the database design with denormalization, that's kind of a reverse process of the normalization. So I think we in the in the relational data model, we discuss what is a normal forms and what is a normalization process. So the whole idea behind the normalization process is to try to, for example, to reduce the redundancy existing in the data, and then to split the table into smaller ones based on the semantics of the attributes, relationship among the attributes. For example, relationship among attributes might be defined by functional dependency. So, but at the end, so the normalized table will allow us to retrieve the data and without any force. The database does not store the redundant data. Second one, when we join the smaller tables into the bigger one, and the bigger one should contain the accurate information about the data. So for the denormalization, that basically means that instead of split a big table into smaller ones, we're going to join smaller tables, a set of smaller tables into a bigger one. So I think the main purpose of the denormalization is very similar to the views. So once we do the denormalization, we pretty much merge related smaller tables into a big table. And then the user can go to the big table to retrieve the information they need. Okay. Otherwise, they have to join those smaller tables to produce the query result they want. So this is considered very expensive. So the denormalization, I think this whole process is mainly used for performance consideration. Okay. So let's see the first one, the denormalization. So I think we have already discussed what's the denormalization and why denormalization might be useful. So it's mainly useful that if a lot of queries requires to join a set of tables together to produce the result, then if the join of those set of tables is expensive and consume a lot of time, then you may consider using the denormalization process. Means that you, instead of maintaining smaller tables, you join the smaller tables into the big one, and then you just maintain the big table, so that the user can go to the big table directly to get the result they want. Okay. So some tips of denormalization is that do not automatically assume that all joins will take too much time. So it's really depending on the type of joins and also the attributes, the properties of the attributes that that needs to involve in the join. And also in many cases, joins are the most efficient access method. So despite the overhead they require. So I think this kind of a denormalization really kind of inspire us that whenever we make some decision, we have to probably examine the cost and the benefit, and then to see even the join is very costly, but the join operation can bring much bigger benefit than we probably want to do the denormalization. So pretty much we have to assess the cost and the benefit of denormalization and then determine whether we want to do the denormalization or not. Okay. Then the customized data views. So the views in the simplest term can be considered as a temporary table that contains a query result. Okay, So the reasons for using views is that we can control users' access to the data. So instead of allow the user to access table directly, we direct them to the views. So then we can define the views to determine what kind of columns and what records of that table that user can access. So that's basically the reason why we use views. And also, one thing we need to be aware of that views are synchronized with the base table from which they derive. So that means that if we try to insert tuples into views, then those insertions will most likely reflect it into the base table that views is derived from. Then regarding who can create views, the owner of the tables, they can create views. The users with administrative privilege at the database level, they can also create views. And also users with necessary privilege. So in this class, we won't be able to study the database administration. So that's why I think we just basically assume that if we are able to create views, then what we should be careful, or what we should consider to make the views. I mean, the views can really handle the database updates correctly and efficiently. Okay. Index, in the simplest terms, is a data structure. It stores the location of the record, of a single record or collection records that's stored in the physical storage. Okay. So the index can pretty much help the access to the database data much faster. And also index, we can also use index to ensure the uniqueness. For example, if we build index on the, for example, the primary key field, well, then we can use index to make sure that every primary key will have a unique index. Okay. And also its index can enable clustering, so we can build index for each individual record, or we can build index for an attribute for the records whose attribute value may fall into a range. So in this case, we can form the clusters of the records and then build the index for each cluster. So let's start study the view. So a view is considered as a virtual table whose data is the result of a stored query, so standard SQL query. So it is derived each time when you query against the view. Okay. So your view it will be computed on the fly. And if the base table does not change frequently, I think the view will be stored and then will be pretty much keep the same. But if the base table changes, then the view will be changed accordingly. So that's why the nice feature of the view is that it is synchronized with the table that view is dependent on. Okay. So in order to create view, we use create view statement. So we have create or replace view. Then the view name, we give a view name, then an as, then followed by as. That's a standard SQL query. So start with select statement. Okay. So this query can be simple or can be very complex. The query can involve in one table or multiple tables, depending on the situation. So this slide shows an example of the view. Okay, so first, I think we can ignore this part. So first, we assume that we have two relation space tables. So we call the cars and the brands. So cars, we have car ID as primary key, car name, and the brand name. And the brands, we have brand ID and the brand name. Sorry, the cars has brand ID. So basically, here we can hear that there is the foreign key and reference key here. Okay, so the brand ID of the cars is a foreign key reference to the brand ID of the brands table. So these two commands are simply create branch table and cars table, okay? So here we can tell that when we create table, we also define the primary key constraint for the branch. And also we can also we have some other we call the column constraints. So we can this not null applies to the brand name. And for the cars, we kind of specify the constraint for the car name, brand name, so none of them can take the null values. And also we specify the primary key for the cars, that's with the car ID. And finally, we also specify the foreign key. So brand ID of the cars is the foreign key reference to the brand's primary key. And this onDelete cascade, basically, it's kind of a define the deletion behavior. So it means that if we have to delete some records from the brand table, so we know that the brand for a record, its brand ID might be referenced by some records in the cars, okay? So if that is the case, if we delete some records from the brand and whose brand ID is referenced by the records in the cars, then this onDelete cascade means that if we delete records from the brand, then all the records in the cars, okay, reference the brand ID of the deleted records in the branch table will be also deleted at the same time. So by doing so, we really can maintain the foreign key constraint. So it means that after the deletion, we won't have any records in cars whose brand ID becomes invalid. The reason it becomes invalid because we will not be able to find any records in the brand who have the same brand ID, okay? So that's why this onDelete cascade just means that if we delete records from brand table, we also need to delete the records from cars table who reference the deleted records in the brand, okay? Then at this kind of a small kind of statement showing that how we can define view. So we create view, the view's name called cars underscore master. As so we select car ID, car name from cars. Okay, so in this case, this view actually is solely specified on the cars table. Okay, so that's basically how we can create a view. So we just show this example. So here we create cars master that solely depends on the cars table. We also create all cars view. So this view actually is a joint result of the car table and the brand table. Okay, so we join these two tables on the condition that the two tables have the matching values on the brand ID. And then we basically list the car ID and the car name, that's from the car table, and the brand ID and the brand name, that's from, I think. In this case, the brand ID is still from car table, but brand name is from the brand table, okay? So in this example, all cars is a view that is derived from two tables. So in this case, when we're talking about the views are synchronized with their kind of associated tables, that means that if something changes in the cars, then all cars, this view will be changed accordingly, okay? If something changes in the brand, the same thing. So it means that if there is a change in one or both tables, then all cars, these views will be automatically changed. So it means that the content of the views will be synchronized with the contents of the table that they depend on. Okay, then we can use standard SQL query to extract information from the views. So for example, we can select car ID, car name, brand name from all cars. So pretty much we treat the views and the table roughly the same when we try to retrieve the information from the views or tables. So we can also have a query that can involve both views and the tables because views can be considered as a temporary table store. synchronized temporary table that stores some query results. Then we can also, join the views with some base table, or even we can join views with another views. Okay. So here, give you one example, like we join all cars, that's a view, with customer table. So we assume that if we have customer contains customer name, customer ID, and I think customer ID should be the primary key. Okay. In this case, we're trying to find the customer name who pretty much own a car that the brand name is Ford or manufacturer is Ford. So we can also renaming attributes when we create views. So because a view is defined by SQL query. So in the SQL query, we do have select statement. Okay, those select statement determine number of the columns and the names of columns in the resulting table. Then if when we create a view, if we specify the attributes in the view, then pretty much means that instead of having the car ID, the car name in the view table, we will going to have ID and the name in the view table. Okay, so that's kind of renaming attributes of the views during the creation of the views. So that's pretty straightforward. Okay, now we come into a DB series business. So we know that views are synchronized with the base table that the views rely on. So for example, if we insert records into the views, and then usually the insertion will be propagated into the base table. If we delete, the same thing. So pretty much means that if we update views, then those updates will be synchronized in the base table. So it's very similar, like if we update the base table, the views content will be changed. Here the same thing, if we update views, then the base table that views are built on will also be changed or updated. So then there may be a lot of considerations we need to think about, okay? So the first one, for example, if we drop view cars and the schoolmaster. So I think in this example, since cars and schoolmaster pretty much rely on two tables, I think in this case, this drop may not affect the base table, okay? Because it's not have one-on-one association. So basically means that if the updates on the views, if it can propagate into its base table, then that should be one-to-one mapping. So one record in a view will be mapped to the one record of a base table. If there's this one-to-one mapping, then the updates can be propagated from the views to the table. If not, I think now the database will not allow those changes to be propagated. So here we have a concept of the updatable views. Okay, so the updatable views means that modifications on views are allowed if the view is defined by selecting some attributes from one relation. Okay, so it means that only updatable views, their data can be updated, and we do have restriction on updatable views. So first one, the views should be contain attributes from only one relation, and we also have several other constraints. The first one, the where clause must not involve R in the subquery. Okay, so first, there's no R, the same relation involved in the subquery in the where clause. Second one, in the from clause, we can only consist of one occurrence of R and no other relation. So basically means that in the from clause, we only have R one table, no more. Okay, so it also means that we will not allow the self-join. Okay, then in the list in the select clause must include enough attributes for every tuple inserted into the view. So I think this basically means that the attributes we need to have at least to have the primary key Okay, if we don't have the primary key attributes of the table, then when we update the view, then there's no one-on-one mapping between the view record and the base table record. Okay, so that means that the select class must have sufficient attributes so that we can maintain the mapping, one-on-one mapping from view record to the base table record. Then an insertion, deletion, and update on updatable views can be applied directly to the underlying table. Okay. Then for all the views that are not qualified as updatable views, then I think depending on the implementation. So if the database will restrict that only updatable views can be updated, then I think those updates will be automatically reflected to the base table. And then we will not have worry. But if the database does not distinguish the updatable views and non-updatable views, and try to synchronize views updates with underlying table updates, then there are going to be some trouble. So then we have to maybe implement some procedures to, either to modify the updates on the views so that the updates on the baseline table will be correctly conducted, or we may deny updates on the views so that there's no inconsistency between the view records and the baseline base table records. Okay, so now we kind of see there's some kind of fundamental examples, the motivational examples that we can discuss to really think about why we need updatable views, why do we need to distinguish the views. So still assume we have two base table, cars and brands, and we create two views. One is car and schoolmaster. So this is mainly based on the cars. The other one is all cars. So this is actually based on the cars table and the brands table. So at least from the updatable views definition, the all cars will not be the updatable views because in the from clause we have more than one table. Okay. If you go to the car and the schoolmaster, I think this view can be considered as updatable. Why? Because first it has only one table cars in the from clause, and then we need to check. And also there is no nested query in the from clause. In the where clause, we don't have where here. And then we have to examine for the car ID and the car name. Okay, so are these two attributes enough to uniquely identify a car? So I think it really depends. I think because car ID is the primary key, so then the car ID and the car name, given the car ID attribute, we should be uniquely identify one record in the cars. Okay. Then let's see the original. I think we do have a create table command. So we have cars. Okay, brand ID is not enough. Okay, so that's basically the more like a constraint for the brand ID, means that for every record in the cars table, the car ID is the primary key, so it's not null. Then the remaining car name and the brand ID, both non-primary key attributes, also have constraint, not null. Okay. Now let's go back to the example. So if we delete on the car master, so then it will delete on the cars. So when we try to delete a record in the car master, that's the view table. If we specify, for example, the car ID. Okay, since car ID is the primary key of the cars, so car ID equals to 1, definitely will be referring to one record in the cars. Okay, and the things, the cars and the car masters, those are synchronized. So for the record in the view table with car ID equals to 1, will point or corresponding to one record in the cars table, that is car ID is 1. So when we delete the tuple from the view with car ID equals to 1, then the database know exactly where to, which record from the car's base table will be deleted. So this deletion on the view table car's master should be fine, okay? Then if we update on the car's master, this view, for example, we run the update car's master, set car name equals to Ford Mustang, and the car ID equals to 2. So these updates will be also good. Why? Because it's delete for specific record with car ID equals to 2. So for a record in a view table with car ID equals to 2, that record you pretty much synchronized with only one record in the cars table with car ID equals to 2, because there are no two records with the same car ID value since car ID is a primary key. So in this case, if we run this delete update statement, then the database know exactly which record in the cars table need to be updated. Okay, so the updates will be fine. Then how about the insert on the cars master? Okay, so if we insert into cars master values, I think the Ford Mustang, this value, I think this probably the, let's say the, because in the views we do not have the primary key defined, so we may have car name. Okay, so if you do not have primary key defined, so this insert cars master car name means that although there are multiple attributes in the car's master view table, and since we only specify the car name, that means we only specify a value for the car name attribute. So the remaining attributes we take null value. So this command perform on the view table cars master is okay. Okay. However, this insertion will cause trouble because when we try to insert a record in the car's master, we only have the car name, we don't have car ID. Okay. So then if this insertion is propagated into the cars table, then we end up, we have a record only has car name as Ford Mustang. We don't have value on the car ID, we don't have value on the brand ID. So if we have a null value on the car ID, that will violate the primary key constraint, okay? So that's why if we only insert the Ford Mustang into the view table, then this insertion will have trouble because we will not be able to insert the same record into the cars table without violating the, in this case, the primary key field is null value that indicates entity integrity constraint. Okay, so I think this example, this slide just shows motivational example to tell us that when we create views and if we try to update views, there may be some issues involving those updates. We should be careful, okay? So in the best scenario that we want to have all the views are updatable views. But I think in this case, the cars master still consider, according to the listings must include for every tuple insert. Okay. So in this case, I think this cars master is not considered updatable views in the sense that it only has car ID and car name. It does not have brand ID. When we create the base table, the cars, the brand ID is not null. So it means that if we insert a record into the cars, we must have the brand ID information. And if you recall this, these views, it does not have brand ID. That means if we insert a tuple into the car master view, and if this view is this record is trying to insert it into the cars table, it will cause error because the brand ID is null, which is not allowed according to the constraint on the brand ID attribute. Okay. So let's see some more examples on the view update. So I think this will be one like a very good example. It's coming from the textbook. So assume we have two tables. Movie table contains the title of the movie, year of the movie, length in minutes, run, studio name for produce movie, and producers maybe ID or produce number. Then we have movie executive table. It contains the executive name, address, and the cert number. I think this may be certification number or license number. So that's has the same semantics as the producer number of the movies and the net worth. Okay. So then, because these are two tables, then we create two views. One is create view Paramount movies as select title year from movies where studio name equals to Paramount. So in this case, this view only contains movies that are produced by Paramount. The second one creates view movie production prod as title name, title of the movie, and the name of the production company, and movie join movie with movie EXEC. Then producer number equals to cert number. So we are pretty sure that this movie prod is not. This is not updatable views. Okay, and this one, it does satisfy that it has only involved one table. In the where clause, there's no nested query. But then when we come into the title and the year, so it's depending. So I think the title and the year might not be enough for uniquely identify each record in the movies, especially if when you create movies table, if you have some constraint like the studio name, producer number should not be null for the records in the movies table, then this title and year will not be enough. Okay, so and besides, there are some other issues for creating this view when we try to update, like insert and delete record. For example, when we insert the Paramount movie, so since this view only has two columns, two fields, title and year, so then we just insert Paramount movies values Star Trek in the 1979. Okay, so accordingly, this record will be propagated into the movie table. Okay, so later, if we try to query, select all the records from these views, this one will not be included. This newly inserted record will not be included in the result. Why? Because when we insert this record into the view table, it will automatically insert it into this movie table. Since the view has only two fields, title and year, so then this new record in the movie table only has values for the title and the year, but the remaining fields we have now. Okay. Then when we query this view, because the movie has been updated, then the view will be reproduced again. Then the view will be run again. Then since view has studio name equals to Paramount, that newly inserted record does not have kind of producer studio name as Paramount. So that's why this record, although inserted into the view and then will be propagated into the base table, will not be showing up if you query the view after the insertion. Okay, so that's the problem. Okay, so in order to fix this problem, then you probably have to, when you create view, you probably have to include the student name. Okay, so that when you insert into the view table, then you're going to pretty much specify the studio of each movie in the view table. Similar thing can be happen for the update. For example, when we delete from Paramount movies, where title like the percentage track, so means that for the movie whose title contains track in it, then we will going to remove those movies. So we are trying to remove the movies from the Paramount, okay? This from the Paramount movies from the views, and this will be propagated into the base table, okay? So then it may cause deletion of movies not from the Paramount. Why? Because we only delete, for the deletion condition, we only focus on the movie name, okay? So it is possible that in the movie table, there are some movies contains track but not produced by the Paramount. But since this movie satisfy this condition, then they will be removed, they will be deleted from the movie table at the same time. So then, in order to make sure that when we try to delete the record from the Paramount movies view, we only delete records from of the movie that produced by the Paramount. Then the possible fix that when we delete, run the deletion, we have to have the add one actual condition in the where clause. So we have to specify the studio name equals to Paramount. Okay. So in this case, then we are able to delete it, the records from the Paramount movies without causing any trouble. Okay. So I think then the question comes to, you either have to remind the users, you have to have the fixed like template for the users to perform the deletion on the Paramount movie views, or you can implement a trigger. So this trigger basically will watch out all the deletion or updates or insertion on the Paramount movies, and then we automatically, for the insertion, we add the studio name equals to Paramount. For the deletion, we automatically add this condition in the where clause. And also for the update, I think the same thing. Okay, so that's kind of what we can do. Okay, the update is the same thing. So if we try to update Paramount movies, year equals to 1979, title equals to Star Trek, the movie. So in order to be safe, because if it is possible that the same year that the same title of the movie has been was produced, but by a different studio, then this deletion may cause the movies that produced by the studio other than Paramount be deleted also. So that's why we in the update, we will update also. So that's why we have to, in the update statement, we have to add actual condition to make sure that studio name equals to Paramount. Okay. So that shows the strategy that if you have to, when you create views, you have to examine what the behaviors or the updates on the views. Then you probably have to fix some queries by adding some actual conditions in the query, in the update queries on the view table, so that we can have kind of an accurate update on the base table too. Okay. So since we didn't cover the PLS called programming considering time issues, so that's why this code, I still want you to know that probably one better solution is that we're going to use trigger. So the trigger is a mechanism, database mechanism. So once we create it will run in the background forever. Okay, so trigger always looking for a triggering event. A triggering event can be the insertion, update, or deletion on a certain table. Okay, so then we can create a trigger that watch out on a specific view table. Okay, then we basically, depending on the triggering event, if this is insert, then when we insert the the records into the views, we're going to, because that insertion will be automatically propagated into the base table. So we're going to revise the insertion of the base table. So by adding the studio name into the record. Okay, so that's kind of the trigger that we can use. So we can also create trigger to modify the query for the update on the Paramount views table and delete on the Paramount view table. Now let's see the views versus materialized views. So materialized views are kind of a pre-computed. So views will be computed first time it is called, okay? And the materialized views will be pre-computed without the calling of the views, okay? So without, the query on the views. So that's called a materialized view. But then when we create a view, we can either create a normal view or the materialized views. That's really depending on the situation. And here it shows the kind of different situation that we can either use view or materialized view. So views are used when data is being accessed infrequently and the data in the table gets updated on a frequent basis. So that's basically the situation that the view is not used very frequently, but the base table that's related to the views are frequently updated. So this case is not worth of pre-compute the views, because you pre-compute the view for this moment, it may be obsolete for the next moment because base tables change. Okay, so in this case we use general view table. So when we create view, we just create view. For the materialized view, that's usually will be used for the situation that the base table is not changed frequently, and then the views has been accessed frequently. Okay, or the base table has been accessed frequently. If the base table has not been changed frequently, that means that data is pretty static. Then we can compute the views, and that view may hold for a longer time because view only change when the base table change. Okay. Then also we pre-compute the views because there are a lot of requests of to access the data on the views. So if that is the case, you're going to use materialized views. Okay. And this slide shows how to create a general view and a materialized view. So I think just the create statement is a little bit different. So one is called create view, the other one is called create materialized view. So if you look at the query, both are the same. So, but it does have differences, means that you're going to use create view if the view is not accessed frequently. The content of view is not accessed frequently, and the base table is changed frequently. Then you want to use create view. You use create materialized views if the base table, seldom change, and this view table has been accessed frequently. Then you want to use materialized view so that you can pre-compute this query result and then provide the content of this view to a lot of queries over maybe a relatively long time. So that's considered efficiency. Okay, good. So next one, we're going to study index. So index, when we create a physical database, we also need to consider index. So we need to analyze to see if we really need to create index and to speed up the search, the records in the database. Okay. So what is the index? So index is considered as a data structure. So usually we create an index either on the single attribute or on the combined values of multiple attributes. And the main purpose of creating index is to speed up the search of the records in the database and also speed up the query execution time. So in the index, we're going to have a search key that is the attribute or set of attribute used to look up the records. Okay, an index is considered a data structure. It contains more like an array. So each Each element of the array contains at least two fields. One is the search key, the other one is pointer. So this pointer actually points the physical location of the records whose attribute values match the search key. Okay. And the one thing you need to be aware of that the index files are typically much smaller than the physical data file, especially for the big data. So that's why it's using index really provides convenient and a quick access to the data, especially the big data. Okay. So there are two basic kinds of index. One is the ordered index. So that means that the search keys are sorted in the sort order. Okay. The hash index basically means that we build the hash value for the search key. Okay. Then pretty much we use either hash table or hash map to store the hash index. So this shows the motivation for the using index. Okay. So when relations are very large, it is very expensive to scan the relation in the our record in the relation to find the records that satisfy certain conditions. So for example, consider that we run this query select star from movies where studio name equals to Disney and a year equals to 1990. Okay. So assume that there are 10,000 tuples, of which only 200 were made in 1990. And if we build an index on the year, okay, then only 200 tuples with year 1990 will be examined. So what does that mean? Means that when we create this movies table, we create an index built on the value of the years, okay? So if given this query, it does query the year. So then we can use index file to find the records whose the records with the year as 1990. Okay. Then we go to those records to find the corresponding location of the record in the table, in the base table. Okay. So in this case, instead of if we do not have index, we have to examine roughly all. In the worst case, we have to examine all 10,000 records to find which movie satisfy the year equals to 1990 and studio name equals to Disney. But with index built on the year, if we assume that there are about 200 movies made in the year 1990, then instead of examining all 1,000 tuples, we only need to examine, for example, the 200 tuples to find the tuple that satisfies the studio name equals to Disney. So this kind of dramatically reduce the number of the records we need to examine to produce the results for this query. So that's kind of why the index is very important and also very efficient. So when we build index, so in practice, we may have table contains a lot of columns. So then if we want to build index for each individual column, that will be very expensive. That will be very expensive because once you when you submit the query, then the index will be fully loaded into the memory or partially loaded into the memory. So if you have a lot of index, that definitely will consume the memory space. The memory space of your database. That might be negatively impact the running time of a query. And this is the one thing you need to consider. The second one is that every index built then makes insertion of the record deletion or update records more expensive, kind of time consuming, because if we insert a record, we have to update the index file. If we delete a record, we also have to update the index file. If we modify a record, if the fields that we are modifying are indexed, means they build the index on those modified fields, we also need to update the index file. So that's why if we build a meta-index on a single table, then we pretty much will kind of for the insertion and deletion, for sure, we have to update all the index. So that will be very, very expensive. So that's why in practice, usually you're going to build the index based on the query analysis. So you're going to review what are the most common queries will be submitted to your table. Then based on the common query, you're going to pick the attributes that only limited number of attributes that can benefit those common queries, okay? And also, when we can also use a simple cost model to evaluate how index will help us. So, for example, if we have multiple different queries, then the frequent queries, then depending, for example, the percentage of the total queries belongs to one, each individual query, then we probably can measure and to examine which attributes that we build index will most benefit all the queries, okay? Or at least will overall will reduce the running time of all the queries. So in this simple cost model, we have tuples of relation that are stored on many pages of disk. So for the disk is a storage medium, so it's organized data into the page. So a page, I think, should be should be kind of in the kilobytes. So it's partitioned the disk space into the unit of the page. Okay, so each page may have kilobytes of data. And each page may hold many tuples. So this, for the database, does not have the field contains a big data block. So this shows kind of selection of the index. For example, we still have the same example about movies. So we assume movies have an index on title. It is stored on 100 disk pages and with 100 tuples per page. So because when the disk reading the data, it's in the unit of the pages. And also when the memory, so when we load the index into the main memory, and also the data, the unit transferring the unit will be in the pages. So usually we do not pick one record from a disk to the load to the main memory. We usually will pretty much retrieve the whole the data of the entire page and then to the main memory. So assume that 3 tuples have titles as King Kong from years 1933, 1976, and 2005. So it is possible that 3 tuples are stored on 3 different pages. So this shows that the disk pages, okay? Assume an index was built on title attribute. Okay, so index built on title attributes. So this kind of index file, okay? So then for the title King Kong, then it's, I think this drawing is a little bit, okay. So if it's built on the title, then it's for the King Kong, it's supposed to have 3 entries. So 1 point to this page, 1 point to the second page, 1 point to the third page, okay? So the query select star from movies title equals to King Kong and the year equals to 2005. So it means that the database need to load, these pages, and then check their year, and then find out the one that match the year equals to 2005. So that means that it will bring 3 pages, these pages into the memory for the checking. And sometimes we also need to bring 1 page of the index file into the main memory. So finally, I think because in the database system, the disk I/O is considered the most expensive operation. So in this case, we can consider this query will involve 3 disk reads. So it means we have I/O. So we load 1 disk page from the index file, and also we load 3 pages from the data file that contains King Kong. But still, total in 4-page disk I/O. But if we do not build index, then we have to examine all, roughly, I think, if in the worst case, only if we know that if there's only one movie that King Kong in the year 2005. So if that is the case, on average, we have to bring like half of the total pages, like 50 pages. On average, sometimes we maybe bring more pages to find the record we need. Sometimes we may need to bring lower numbers if we're lucky. Sometimes we may need to bring all 100 pages if the record we are trying to look for is stored in the last pages. So that's why on average we can roughly estimate on average we need to access half of the disk pages, so about 50 disk pages to find the data we need. So compare 50 disk I/Os with 4 disk I/Os, I think 50 is much, much higher. So 4 is much, much lower. So that's really reduced the time for the query execution time using the index. Okay, so I think here I want to stop here. So next class we're going to finish the index discussion, and also I think the plan for the remaining semester is that we spend 1 more class on the physical storage, and then I think we can discuss a little bit on the data mining. I think we can spend 1 class, 2 class on data mining. And then we still have 1, I think I probably have spent 1 class on the NoSQL and the Mongo database and the basic. Then I think that's pretty much for this semester. So this semester we do not have term exam, but we're going to have 1 an SQL query project. So I'm trying to finish it by this week. If not, it should be early next week. So then I think you have about 3 weeks, at least 3 weeks to work on the SQL query project. I think that's pretty much the plan for the remaining of the semester. So any questions?